Okay, so we're going to continue our discussion on kinetics today. And what we're going to look at is how molecules actually collide and react with one another. And you see here there are three factors that affect how fast a reaction takes place, or the rate at which it takes place. First factor you see is the rate of collisions between reactants. How quickly are they colliding with one another? How frequently are they coming into contact with one another? Because obviously reactants have to come into contact with each other in order to change and produce a product. Second is the percentage of collisions with the proper orientation that could produce a reaction, because molecules have to collide with a proper orientation. They have to be oriented in such a way where maybe the slightly negative end of a molecule is going to be attracted to the slightly positive end of a molecule. If a slightly positive end comes into contact with another positive end, they may repel each other, and you don't even have a collision for a reaction to take place. So they have to be in the proper orientation. Just like maybe you and your friend might be walking in the hallway a few feet from each other, but if you got your back turned to each other, you won't even see each other. So orientation is important. And then third, the percentage of collisions possessing enough energy, i.e. activation energy, to produce the reaction. Okay, so we have to have enough collisions take place between reactants. We have to have the molecules oriented correctly, and we have to have enough energy coming into contact between the two molecules in order for a reaction to take place. So really there's a number of things that need to happen for a reaction to take place. It's not necessarily just the fact that, well, two molecules are close to each other so a reaction will take place. But it's the rate, it's the orientation, and it's the energy. We can increase collision rates by increasing the concentration and increasing the temperature, because if we increase the concentration, there's just more of the reactants that are going to come into contact with each other, and the temperature gets them moving faster. So the important thing is, as you see down here in red, now every collision triggers a chemical reaction. They have to have a lot of things occur in order for those to happen. So here we have an example of NO2Cl, which decomposes to NO2 and Cl. And they show you the molecules here, how they might orient themselves. And in order for this molecule to produce Cl2, you obviously have to have two chlorine molecules, or two chlorine atoms, come into contact with each other to pull off and form that molecule. So as we see up here, if they orient themselves in this way, the oxygen really doesn't have anything to do with the chlorine. It really doesn't want anything to do with the chlorine. And the two nitrogen and two oxygen here aren't going to do much with each other. So in order for this reaction to take place, the two chlorine atoms have to knock into one another. They have to collide with one another in order to get pulled off, and then that leaves the two NO2 molecules. Here. So this is an example of orientation needing to be happening correctly in order for the reaction to take place. Now this is a potential energy diagram, and we've seen these before throughout the year. So here we have a reaction up here. We have A plus B, or AAB plus C yields A plus BC. This is a single replacement reaction. And so we have this AB molecule here and C down here as the reactants, and this is the energy level that they are occurring at. Now, as the reaction takes place, there is a time where all three substances are bonded together. Because remember what's happening here, C is coming to replace A in this case. So C wants to kick A out and bond with B. Well, at a time, C is going to be bonded to B as well as A is bonded to B, because C wants to be bonded with B and A wants to be bonded with B. So there's going to be a moment in time where we're going to have an ABC molecule, where both C and A are going to be bonded to B as that goes on. That increases the potential energy. So the kinetic energy, when they collide, boom, it's converted into potential energy. So that's increasing the energy. Now we get to the top of this, mound here, if you will. Actually, we'll just look at this here, the top of this hill. This represents the amount of activation energy, this E sub A. This represents the amount of energy needed for C to collide with this molecule in order for the reaction to take place. So if C kind of comes in and kind of bumps into them, but doesn't provide enough kinetic energy to convert to the potential energy, it might go up this hill and not have enough energy to get over the hump, so to speak. If there is enough energy to get over this hump here, then the reaction will take place, and the products will be formed usually at a lower energy level than what they started at. So the distance from the energy level that the reactants start at up to the top of the hill, we call that the activation energy. And in order for a reaction to take place, we have to supply an activation energy equal to or greater than the activation energy of the reaction. If you see the energy of the collision is less than the activation energy, the reaction will not happen. It has to be greater than that. So these will go up the hill, and if they just make it this far, it won't happen. Just think of a ball rolling up that hill, and if a ball doesn't have enough energy to roll up to the top of the hill, it's going to fall back down. Okay. The higher or the more activation energy that you're going to need, generally these are going to occur at a slower rate. And if you think of these as hills, climbing up a bigger hill and coming down the other side, you're generally going to walk slower up because you have more distance to go and more energy to use. Now, a smaller hill, the reactions will generally happen at a faster rate. Okay. So as you see down here, generally speaking, if less energy is required to get over the hump, more reactants will collide with enough energy. So we measure that activation energy, and then we can use it in a diagram like this to give us a picture of whether or not that reaction is going to take place. Okay, so in summary, 3 things have to happen. There must be a collision between the molecules. The collision must have the proper orientation to yield a reaction. And 3, we have to have enough energy. The energy of the collision must be greater than or equal to the activation energy of the molecules in order for the reaction to take place. Okay. Now this picture gives you the difference between an exothermic and an endothermic reaction. Exothermic reactions are going to give off energy. So the reactants are going to be at a higher energy state than the products. In an endothermic, they're going to need to absorb energy. So the reactants are going to be at a lower energy level than the products. Okay. And we've talked about that many, many times before. We can talk about the activation energy of a forward and a reverse reaction as well, because remember, all reactions are reversible. So if we take the potential energy diagram of the forward reaction that we looked at earlier, the AB plus C, and we place a mirror in the middle of it, this is the potential energy diagram of the reverse reaction. So the reason that this reaction proceeds from AB plus C to A plus BC is because there's less activation energy going forward in the reaction than there is going in the reverse direction. This is why normally some reactions will go generally easier one way than the other. So if the activation energy is a certain amount in the forward reaction, it's going to change values in the reverse reaction. It'll probably be much larger. See, the difference is, let's see, from here to here versus from all the way down here up to here. You're going to have a much larger activation energy going in the reverse of this reaction than you did in the forward. And then that brings us to the infamous Arrhenius equation, which is more or less a y equals mx plus b equation. As you can see there, K is the rate constant, E sub A is the activation energy, you have the R constant, you have the absolute temperature, and then you have A, which is a constant that's related to the frequency of collisions. Okay, and there's how it correlates to the y equals mx plus b equation. Really don't need to know much about the Arrhenius equation for the AP exam, thank goodness, you're saying as you're looking at it. But this little equation down here at the bottom, slope equals negative activation energy divided by R, that can be helpful in some of the problems we're doing. But as far as the Arrhenius equation itself, don't really need to use that a whole bunch. If you're given data, as you have been, and you graph it, as you see here, you take the natural log of the K value, the rate, over the reciprocal of the temperature, and you get this straight line here. In order to find the activation energy, we could find the slope of the line. And you see the slope's -1 times 10 to the 4th. Okay, that's easy to do. And then to find the E sub A, the activation energy, we're going to take the slope times the R value. So just simply take the slope off the graph times the 8.314, we're using that, R value, and as you see, the activation energy ends up in 83 kilojoules per mole, or 83,000 joules per mole. And that activation number will be quite high. It'll generally be a pretty high number. So I don't think we have to worry so much about the equation, but understand that the slope is equal to the negative activation energy over the R value. And so if you have a graph and you're able to find the slope, you can easily calculate the activation energy then of that reaction.